Have you ever just paused, really looked around, and wondered how truly miraculous your eyes are?
Mm-hmm.
Or perhaps pondered why the sky is that vibrant blue on a clear day? Or, what cosmic dance makes stars appear to twinkle at night?
While planets don't. Yeah,
It's pretty astonishing when you actually stop and think about
it
it.
really is.
Well, get ready, because today's deep dive is all about the human eye, its incredible mechanics, and, well, the fascinating optical phenomena that literally paint our world with light and color.
Sounds great.
We've gone through quite a stack of comprehensive sources, everything from really detailed scientific explanations to some quick reference guides, basically, to bring you the most important nuggets of knowledge.
Right.
Our mission here is sort of to give you a shortcut to being well-informed, providing those aha moments that might just have you truly seeing the world a bit differently.
Absolutely. And it's true, when we talk about our senses, the human eye really stands out. It's one of the most valuable, most sensitive organs we have.
And it's unique, right, in how it sees color.
Completely unique in its ability to identify and perceive colors. I mean, no other sense can do that on its own. Imagine trying to identify yellow by, I don't know, touch or smell.
Huh? Yeah, impossible.
Oh.
And what's really striking when you start to unpack the eye's design is just how much it mirrors a camera. It's like nature built the perfect little photographic device.
Exactly. That's a great analogy. At its core, the eye's lens system is precisely engineered to form an image on that light-sensitive screen we call the retina.
Like film or a sensor.
Kind of like that, yeah. It's a remarkable parallel to how a camera works, but honestly, infinitely more complex and adaptable.
So if it's like a camera, what are its key components? Let's start right at the very front. What's that transparent bulge we actually see?
Okay, so that's the cornea. It's a thin, transparent layer on the front surface of your eyeball. The whole eyeball is roughly maybe 2.3 centimeters in diameter.
And the cornea is important for focus.
Hugely important. Most of the bending of light, the refraction that happens before light even properly enters your eye, happens right there at the cornea. It's the eye's main focusing element, really.
Okay. And then behind the cornea, we've got the iris and the pupil. What roles do they play?
Right. So the iris is that dark, muscular diaphragm behind the cornea that's the colored part of your eye.
Ah, right.
Its main job is basically to control the size of the pupil, which is just the opening in the center.
Like a camera's aperture.
Exactly like an aperture. It automatically adjusts to regulate how much light gets into your eye. Whether you're out in bright sunlight or in a pretty dimly lit room.
Clever.
Yeah.
Then there's the crystalline lens. I read it's made of this unique, fibrous, jelly-like material.
That's right.
And its role is pretty critical for focusing on different distances, I understand.
It absolutely is. So while the cornea does most of that initial bending, the crystalline lens provides the finer adjustment of focal length.
Fine-tuning.
Precisely. Fine-tuning. And this is crucial for making sure that objects at different distances, whether it's the distant horizon or, something right up close, are brought into sharp focus directly onto your retina.
And the retina itself, what's actually going on back there?
Okay, the retina. It's this delicate membrane, and it's packed with just an enormous number of light-sensitive cells.
Millions.
Oh, millions upon millions. And when light hits these cells, they get activated, they generate electrical signals.
Little electrical pulses.
Exactly. And then they send those signals racing off to your brain via the optic nerves. Your brain then has the job of interpreting these signals, creating the perception of objects as they are.
Amazing.
But here's a truly fascinating detail. You might find this cool. The eye lens actually forms an inverted, upside-down, real image on the retina.
Wait, what? Upside down?
Yep. The world is literally projected upside down onto your retina. Your brain then seamlessly flips it right side up for you without you ever noticing.
Wow. So my brain is constantly reorienting my vision.
Yeah.
That's genuinely mind-bending.
Isn't it, though?
And speaking of sort of eye magic, how does the eye manage to adjust its focus so quickly, from looking far away to something near?
That's the eye's incredible power of accommodation. It's all about the eye lens' ability to change its shape, to adjust its focal length.
How does it do that?
Well, there are these special ciliary muscles around the lens. When you're looking at something far away, those muscles relax. This makes the lens thinner, which increases its focal length for clear distance vision.
Okay.
But if you quickly shift your gaze to something close, those muscles contract. The lens then thickens, its focal length decreases, and poof, you see near objects clearly. It's an almost instantaneous adjustment.
That makes me wonder, how close can we actually see comfortably? Is there like a limit to that poof effect.
Oh, there absolutely is. For a young adult with normal vision, the minimum distance for distinct vision, we call it the near point, is about 25 centimeters.
About 10 inches.
Roughly, yeah. Try holding a book closer than that and you'll notice it starts to blur or it might cause some eye strain.
Okay. And the far point. How far can we see?
Well, on the other end, the far point for a normal eye is considered infinity, which basically means we can theoretically see infinitely far objects clearly, assuming there's nothing blocking the view, of course.
It's an amazing system, but sometimes it runs into problems, like cataracts. Can you explain that condition a bit?
Sure. Cataracts are a pretty common condition, especially as people age. It's where the crystalline lens, which should be nice and clear, becomes milky and cloudy.
Opaque.
Right, opaque. And this opacity leads to partial or even complete vision loss. The good news, though, is that modern surgical procedures are very effective. They can often restore vision by replacing that clouded lens.
And speaking of vision restoration, I was really struck by the details in our sources about eye donation. That seemed quite powerful.
Yes, it's a truly powerful detail. The fact that eyes can be donated after death, literally lighting up the life of someone who is blind, it's remarkable.
And the eligibility seemed quite broad.
It really is. What's amazing is how inclusive the process is. Eye donors can be of any age, any sex. Even people who wear spectacles or have had previous cataract surgery can often donate.
Even with other health conditions.
Yes, eligibility extends even to those with conditions like diabetes, hypertension, asthma, and other non-communicable diseases. There are criteria, of course, but it's broader than many think.
And the process itself.
It needs to happen relatively quickly. The eyes must be removed within a specific 4 to 6 hour window after death. But the process itself is simple, usually taking only about 10 to 15 minutes, and importantly, it causes no disfigurement.
Wow. And the impact.
It's profound. One single pair of donated eyes can potentially give the gift of sight to up to 4 people suffering from corneal blindness.
4 people. That's
And
incredible.
it really puts into perspective how vital our vision is.
Definitely. But okay, what happens when our eyes aren't quite performing perfectly? When does this amazing system sometimes need a little help?
Yeah, that's when we start talking about refractive defects. Sometimes the eye loses its ideal power of accommodation, leading to blurred vision. There are 3 common types we should probably cover.
Okay.
First up is myopia, which you probably know better as nearsightedness.
Right. So with myopia, you can see nearby objects clearly, but things far away are blurry. What causes that, and how do we fix it?
That's exactly right. The fundamental problem is that the image of a distant object forms in front of the retina instead of directly on it.
Too soon, as it were.
Yeah, focuses too soon. This often happens because either the eye lens has an excessive curvature, it's bending the light too much, or maybe the eyeball itself has elongated slightly.
And the fix? Glasses.
Usually, yes. To correct this, we use a concave lens that's a diverging lens. It gently spreads out the light rays before they enter the eye. This effectively gives the eye's own lens a bit more room, allowing it to focus the image perfectly back onto the retina.
That makes sense, kind of pre-correcting the light path. What about the opposite problem then?
The opposite is hypermetropia, or farsightedness. Here, it's the other way around. You see distant objects clearly, but near objects appear blurry. Your near point is actually farther away than that typical 25 centimeter mark.
And the reason for that? Why blurry close up?
In this case, the light focuses behind the retina. It focuses too late.
Okay.
This can happen because the focal length of the eye lens is too long. It's not bending the light enough, or perhaps the eyeball itself is a bit too short or small.
And the solution here?
The solution is a convex lens, which is a converging lens. It provides that extra bit of focusing power needed to bring the image forward right onto the retina where it belongs.
Got it. Concave for nearsighted, convex for farsighted. And finally, a condition that, well, many of us might face as we get older, presbyopia. What exactly is happening there?
Yes, presbyopia. It's a very common condition that typically develops with aging. It's characterized by a decrease in that power of accommodation we talked about earlier.
The focusing flexibility.
Exactly. People find it increasingly difficult to see nearby objects distinctly, reading menus, threading needles, that sort of thing.
And I'm guessing that has to do with the muscles and the lens getting older?
Precisely. The primary cause is twofold. A gradual weakening of those ciliary muscles we mentioned, and also a diminishing flexibility of the eye lens itself. It just doesn't change shape as easily anymore.
Makes sense. And the correction. Bifocals.
Bifocals are often the most common solution, yeah. They conveniently have a concave part, usually at the top, for distance vision, and a convex part at the bottom for near vision, like reading.
Right.
But our sources also note that contact lenses, multifocal ones, or even surgical interventions are becoming increasingly viable alternatives for presbyopia these days.
It's incredible how we've developed solutions to help our eyes keep seeing clearly. Okay, but now let's maybe zoom out a bit from the mechanics of the eye itself. Let's look at the dazzling ways light behaves out in the natural world, creating some real optical magic all around us.
Absolutely. That sounds like a great transition. One of the fundamental ways light interacts with our world is through refraction, which, as we said, happens in the eye, too. You can see this really clearly with a transparent object, like a prism.
Like a triangular piece of glass.
Exactly. When light passes through a prism, it bends. What's unique about a triangular glass prism is its shape. It causes the emergent ray of the light coming out to bend at a specific angle compared to the incident ray of the light going in. We call that the angle of deviation.
And this bending, this leads to something even more spectacular, doesn't it? The splitting of white light.
It does indeed. We call that phenomenon dispersion of light. It's when white light, like sunlight, splits into its component colors. You get that familiar band: violet, indigo, blue, green, yellow, orange, red, VBGYOR.
Right, the rainbow colors. So why does the prism do that? Why don't all the colors just bend the same amount?
That's the key question. It's because different colors of light actually travel at slightly different speeds when passing through the material of the prism. Because they travel at different speeds, they bend through slightly different angles.
Right.
Red light, for instance, it bends the least. Violet light, on the other end of the spectrum, bends the most. This slight difference in bending angles is what causes them to separate out into that distinct, beautiful spectrum we see.
And we really have Isaac Newton to thank for
Yeah.
kind of cracking this code, right? He was the first to properly demonstrate this whole thing.
He really was. Sir Isaac Newton, yes, he was the first to use a glass prism to actually obtain the spectrum of sunlight. But his real stroke of genius was the follow-up experiment.
What did he do next?
He then took a second identical prism, placed it in an inverted position right after the first one.
Flipped it upside down.
Right. And guess what happened? All those separated colors recombined back into white light. Yes. And this crucial experiment unequivocally proved that sunlight isn't just white. It is, in fact, composed of these 7 distinct colors blended together.
That's brilliant. And that understanding about how white light splits apart, well, that helps us explain one of nature's most breathtaking displays, the rainbow.
It's the perfect natural illustration of dispersion, isn't it? A rainbow is essentially a natural spectrum appearing in the sky, usually after it rains, and you'll always see it formed in the direction opposite to the sun.
Why opposite the sun, and how do raindrops do it?
Well, the tiny water droplets, still suspended in the atmosphere after rain, they act just like millions of tiny little prisms.
Ah.
So sunlight enters a droplet, it refracts and disperses splits into colors right as it enters. Then that light reflects internally off the back surface of the droplet, and finally it refracts again as it exits the droplet, sending those separated colors out towards our eyes. That's what creates those distinct, vibrant colors fluorescing across the sky.
It's amazing to think that every single raindrop is a tiny prism doing that dance.
Oh.
Okay, now let's explore how our entire atmosphere plays a huge role in the light shows we experience every day. I'm thinking about atmospheric refraction.
Yes, atmospheric refraction. It's basically just light bending because of the varying densities and different layers of our atmosphere.
Yeah.
It's similar to how you might see objects seem to waver or shimmer above a hot road surface on a summer day.
Right, that heat haze effect.
Exactly. And this very phenomenon helps us understand something quite poetic: why stars twinkle.
Ah, yes. That's always been one of those beautiful little mysteries. So it's really the atmosphere causing that flickering.
Precisely. Stars are incredibly distant, so they appear to us as tiny, almost point-sized sources of light.
Like pinprick?
Just pinpricks. And as their starlight travels down towards us, it has to pass continuously through our turbulent atmosphere. This atmosphere has constantly changing refractive indices, pockets of slightly different temperature and density moving around. So the path of the light rays varies slightly and erratically from moment to moment. This makes the star's apparent position seem to fluctuate just a tiny bit and its brightness flicker. And that's the twinkling effect we find so enchanting.
But then why don't planets twinkle? They're also up there, shining light.
That's a fantastic question, and it really highlights the difference that distance makes. Planets are much, much closer to Earth than stars are.
Relatively speaking.
Relatively speaking, yes. So they appear to us not as point sources, but as extended sources. Think of them less like a single pinprick and more like a tiny disk, or a collection of many, many tiny points of light packed closely together.
Okay, I see.
So if you consider a planet as a multitude of these individual point sources all sending light our way, the twinkling effect from one tiny point is essentially canceled out by the variations from all the other points. The total variation in light averages out to pretty much zero.
Ah, the averaging effect.
Exactly. It nullifies any overall twinkling effect.
That's a great aha moment right there.
Yeah.
It's all about how big they appear from our perspective, whether they're a point or a small disk.
Precisely.
And what about those extra minutes of daylight we seem to get? The sun appearing before it's technically risen?
Ah, yes. That's another fascinating effect of atmospheric refraction. Advanced sunrise and delayed sunset.
How does that work?
Well, because the atmosphere bends sunlight downwards towards the Earth's surface, towards the normal in physics terms, it makes the sun appear slightly higher in the sky than its actual geometric position, especially when it's near the horizon.
So we see it over the horizon before it's really there.
That's right. We actually see the sun about 2 minutes before it genuinely crests the horizon at sunrise, and we can still see it for about 2 minutes after it has truly dipped below the horizon at sunset.
So we get roughly 4 extra minutes of daylight each day?
Approximately, yes. All thanks to the bending of light by our atmosphere. A little gift from physics.
Wow. Okay, our final optical magic trick of the day ties into something we see every single day, but maybe don't always understand the science behind it. The scattering of light. Can you break that down for us?
Sure, the scattering of light is maybe best demonstrated by something called the Tyndall effect. Have you ever seen, like, a sunbeam coming through a window into a dusty room and you can see the beam itself?
Oh yeah, definitely. You see the dust motes dancing in it?
Exactly. That's the Tyndall effect. It's where the path of a beam of light becomes visible because the light strikes fine particles like smoke, dust, tiny water droplets, or even just the molecules in the air itself in a mixture. These particles cause the light to be reflected diffusely, scattered in all directions.
And this Tyndall effect, this scattering,
Right.
is the reason the sky is blue, isn't it?
It absolutely is. It's a direct consequence of light scattering. The molecules of air, mostly nitrogen and oxygen and other very fine atmospheric particles, are actually smaller than the wavelength of visible light.
Okay, tiny particles.
Very tiny. And crucially, these tiny particles are much more effective at scattering shorter wavelengths of light, which are on the blue and violet end of the spectrum, than they are at scattering longer wavelengths, like red and orange light.
So blue gets scattered more.
Much more strongly, yes. So when sunlight streams through the atmosphere, the blue light gets scattered vigorously in all directions.
Mhm.
Some of that scattered blue light eventually enters our eyes from all over the sky, making the entire sky appear blue to us.
And if we didn't have an atmosphere,
Then there'd be nothing to scatter the sunlight. The sky would look black, just as it does to astronauts in space or on the moon. You'd see the sun as a bright star, but the background would be dark.
wow. Okay, and conversely, this same principle explains why the sun often appears red or orange at sunrise and sunset.
Precisely. Think about the path sunlight takes at those times. When the sun is low on the horizon, its light has to travel through a much greater thickness of the atmosphere to reach our eyes compared to when it's overhead at noon.
A longer journey through the air.
A much longer journey. And along this longer path, most of that shorter wavelength blue light gets scattered away out of the direct path to our eyes.
Filtered out almost.
Effectively filtered out by scattering, yes. This allows the longer wavelength red and orange light, which is scattered much less, to travel more directly through the atmosphere and reach our eyes. That's what gives the sun and the sky near it that beautiful reddish-orange glow.
That's such an elegant explanation for something so common and beautiful. And if we connect this to maybe a practical application, it explains why danger signals are always red, right?
Yes, exactly. It's the same physics at work, because red light is scattered the least by particles in the air, like fog or smoke or even just distance haze.
It travels further without being disrupted.
It penetrates further, remains visible at a greater distance compared to other colors like blue or green. This ensures that danger signals, stop signs, brake lights, warning beacons are seen as clearly as possible, even in adverse conditions, playing a crucial role in safety.
Wow. What an incredible deep dive this has been into the world of light and vision. We've truly gained, I think, so many aha moments from understanding the human eye's amazing camera-like system, its incredible flexibility, to finally getting why we see those beautiful rainbows.
And why stars twinkle but planets don't.
Right. And the actual science behind why the sky is blue and why we get those stunning red sunsets, it's fantastic.
And hopefully you listening feel like you've just gained a quick but a pretty thorough understanding of some really complex concepts. It empowers you with knowledge you can appreciate every day and maybe even share. That's really the power of doing a deep dive into this kind of source material.
Absolutely. So as you go about your day to day, given everything we've talked about, the incredible intricacies of the human eye, the physics of light that allows us to perceive such a vibrant world, maybe take a moment. What new perspective might you gain by simply stopping to observe the light and color around you just a bit more closely today? We challenge you to truly see.